In this lecture, we are going to deal with the development of Schrödinger wave equation. First, we are going to see what is the wave function and why we need the wave function and the properties of wave function, the development of Schrödinger wave equation using de Broglie hypothesis and Einstein postulate. These are the things we are going to concentrate in this lecture. And now we will see what is wave function and why we need the wave function. What is wave function? It is a mathematical function that describes the quantum state of a system, such as particle. The wave function contains all the information about the system and is used to calculate measurable property like position, momentum, energy. And why we need the wave function? We need to explain the wave particle duality and require to describe the quantum system, and also it is used to find the probability. As I said, it is based on two hypotheses. That is a de Broglie hypothesis of de Broglie matter wave and Einstein postulate. These two plays a major role in developing a Schrödinger equation. We have here both particle concept. If we consider the particle concept, then we have to deal with the energy and momentum. A particle means it has some energy and momentum. Wave concept means it has frequency and wavelength. We are going to deal all this energy, momentum, frequency and wavelength. Now we will see some of the important properties of wave function. First and foremost, the wave function must have solution to Schrödinger wave equation. And next, the wave function must be a single valued one. It must be single valued. And the wave function must have a finite value. That is square integrable. We will see it in detail later. The wave function and its derivative must be continuous everywhere. These four are the very important properties of wave function. Now we will see the development of wave equation. That is, it must consistent with de Broglie and Einstein postulate. According to de Broglie, lambda is equal to h over p, not h cross. Remember that h over p, and nu is equal to e over h cross. So also it must be consistent with the energy equation of the particles. That is, the total energy is equal to kinetic energy plus potential energy. Here kinetic energy is p squared over 2m and potential energy is v. So p squared over 2m plus v. And it must be linear. For a constant potential, the desired differential equation will have a sinusoidal traveling wave of constant wavelength and frequency. So we have seen E is equal to P squared over 2m plus V, that is kinetic energy plus potential energy. Based on de Broglie and Einstein postulate, we will rewrite this like before rewriting, we know what is Einstein postulate. E is equal to, maybe I will use a different color, that is E is equal to, according to Einstein postulate, is equal to h nu. What I am going to do is I am going to multiply and divide by 2 pi. So h cross, I am multiplying 2 pi nu and dividing by 2 pi. So this is h cross by 2 pi is, sorry, this is h, not h cross. So h by 2 pi, that is equal to h cross, and 2 pi nu is omega. So E can be written as h cross omega over 1 over 2m. According to T. Broglie, P is equal to H over lambda. So P squared will be H over lambda whole square plus of course this potential energy. Now what I am going to do is I am going to multiply and divide by 2 pi. So H over 2 pi is equal to H cross. This one will be H cross. And this 2 pi over lambda is wave vector k. So this will become H cross squared k squared over 2m plus v. So we got the expression H cross omega is equal to H cross squared k squared over 2m plus v. A wave function psi of x and t that represents a particle of completely undetermined position traveling in positive x direction with precisely known momentum p and kinetic energy E would be expected to have one of the following forms or their linear combination. See, this may be a sinusoidal one. Let us take a sinusoidal wave of fixed frequency. Frequency fixed means energy is fixed. H cross omega is fixed. So energy is fixed, which is equal to p squared over 2m. Since 2m is a constant, p is a fixed one. You can easily calculate. If you know the frequency, you can calculate exactly the momentum. But however, what about its position? The position is completely undetermined because it can vary from 0 to infinite, here to infinite. So it will have a form a sine kx minus omega t or a cos kx minus omega t or a e power I kx omega t or a e power minus I kx minus omega t. It will have one of these four form. First two, the sinusoidal sine and cos is for pound state. These two are for pound state. Maybe I will use different color. This is for pound state. Sorry, this is for pound state. First two is for pound state. Then we can take this as most general. We will see all are valid solution for the Schrödinger equation, and normally we will take this as a generalized solution. We will take for pound state these two. Sinusoidal is generalized solution. Here normally we will take the now in this case we will take a is 1, that is it is normalized wave function. Then we will move on further. We have found that h cross omega is equal to h cross squared k squared over 2m plus v. Now let psi act on this h cross omega psi, then h cross squared k squared over 2m psi plus v multiplied by psi. Now we take this as a normalized solution. Sorry, this is the wave function. Then you keep a as 1, it is normalized. So, what will happen if you take first order time derivative? You will get minus I omega psi. Let us say this is psi. This is psi is equal to e power I kx I kx minus omega t. If you differentiate with respect to t, you will get minus I omega multiplied by this wave function minus I omega psi. Then if you multiply both sides by I, you will get I square is minus 1, minus 1 is minus 1 into minus 1, you will get plus. So the omega psi is equal to I t psi by tt. Then we have to find k square. How you will find k square? You take second order partial derivative. T2 psi over Tx2, then you will get first time if you differentiate, you will get Ik, then next another Ik. If you differentiate next time, then another Ik, which is equal to, if you multiply I squared k squared. I squared is minus 1, so minus k squared psi. You will get minus k squared psi. Then if you multiply by minus 1, you will get minus delta 2 psi over delta x2 is k squared psi. So now you replace this omega psi, by this one. Omega psi by I. Here you have h cross, then t psi over dt. Because I am replacing omega psi by I, t psi over dt. Similarly, k squared. What is k squared psi? You take this k squared and psi, which is equal to minus delta 2 psi over delta x2. So I am replacing. Already you have h cross squared over 2m. Minus h. So here you have minus h cross squared over 2m delta 2 psi over delta x2 plus v psi. This is the Schrödinger wave equation. We have seen that I h cross delta psi over delta t is equal to minus h cross squared over 2m delta 2 psi over delta x2 plus v psi. Let us consider the pre-particle. For pre-particle, the potential energy is 0. This term will go away. Then we will get I h cross delta psi over delta t is equal to minus h cross squared over 2m delta 2 psi over delta x2. Here you can see this energy operator E is I h cross delta over delta t. So if I h cross delta over delta t acts on psi, it will give a energy eigenvalue E, because it's a energy eigenfunction, E multiplied by this psi. Here the right hand side is minus h cross squared over 2m t2 over tx2 psi, which is equal to E psi. This is called time independent Schrödinger wave equation. Since it's time independent, we have changed the partial derivative into full derivative. Now we have claimed that this wave function will be in the form of sine kx minus omega t, cos kx minus omega t, or ei kx minus omega t. Here is since it's a time independent equation, we make t is 0. That means omega t is 0. So we have ignored the omega t term. So the wave function must be in the form of sine kx or cos kx or e power I kx or e power minus I kx or their linear combination. You take sine kx square. What is second order derivative of sine kx with respect to x? You will get to minus sine, we have to take, if you differentiate once, you will get cos k cos x, then if you differentiate again, you will get minus sine k squared. If you take second derivative, minus k squared sine kx. Similarly here, minus cos kx. Of course, if you differentiate kx twice, you will get kx squared. So this is minus kx squared. Similarly here, if you differentiate twice, ik into ik is minus k squared e power I kx. Here also same thing, minus k squared e power I kx minus ikx. If you replace this second order derivative by this term, you will get naturally minus of minus will become plus. So if you when this energy p squared operator, sorry, this is p squared operator is you remove this h cross squared. P squared operator is minus h cross squared. This is p squared operator is equal to minus h cross squared uh, t2 over tx2. If you multiply, if you replace this with t2 over tx2, this is second order derivative. Minus of minus will become plus. So you will get for all four terms, you will get h cross squared, this k squared. Because here also you have one minus, here also one minus, over 2m psi is equal to E psi. So this h cross squared k squared is nothing but your p squared over 2m. This is p squared over 2m is kinetic energy of the system, which is equal to E psi. So this all these four terms are solution for this Schrödinger equation. So these four are acceptable wave function because it is a solution. It has solution for the Schrödinger wave, time independent Schrödinger wave equation. Subscribe to my channel to get my latest videos, and join my channel to support its growth and enjoy the exclusive perks. Also use the thanks button to make one-time contribution and support my channel. Thank you very much.